Okay, so last time we talked about physical properties and chemical properties, and today we're going to talk about physical change and chemical change. So let's think about something like ripping a piece of paper in half. When I rip a piece of paper in half, that changes the paper. Well, it changes its size and maybe, its shape, but it's still paper. That would be an example of a physical change. So the definition of a physical change is a change to a substance that doesn't change the substance to something new. So it's chemically still the same. So ripping paper in half, let's give some examples. So ripping paper in half, so ripping, chopping vegetables, something like that. It's still a carrot. If I chop it into pieces, it's still chemically the same thing. Phases of matter, or changes in matter, like solid to liquid, liquid to gas. When I change the phase of something, it doesn't change the substance chemically. It's still the same substance. It's just gone through a slight change. It looks slightly different. So physical changes are, hammering out a metal, something like that. Putting wood through a wood chipper. It's still the same substance when you're done. So, I've got a paper clip here, and I can bend it all out. I can unbend and do all this stuff to this paper clip. And it's still chemically the same thing when I'm done. I put it through a change. It's not the same shape that it was anymore. So it just went through a physical change. All right, so physical changes aren't too hard to kind of wrap your brain around. Chemical changes sometimes are, because you can't really see, well, we'll get to it. So let's talk about a chemical change. Chemical change is going to be a change to a substance that changes the substance to a new chemical. Like when I burn a piece of paper, it's not paper anymore. It's ash, and that ash is not the same as paper. It looks totally different. So if I were to take, say, in my sugar and my sulfuric acid demonstration that I did in class, I took sugar and I burned it. Well, I didn't burn it, but I combined it with sulfuric acid, and it went through this chemical change. So I took that sugar and I changed it to basically coal, charcoal, and water. And that was a big chemical change, and I know that it was a chemical change because I could see that it looked different than it looked before. So when I made that change to the sugar's white and crystalline, and it tastes sweet, and it's got all these different properties. And when it underwent that change, I turned it into something black and ashy and crispy and water vapor. So, a chemical change. I mean, I turn that sugar into two completely different things than what sugar is. That's a chemical change. I'm going to kind of draw a picture of a chemical change for you. So here I have, this is an equation that's kind of showing you what's happening. So sodium chloride, for those of you that maybe don't remember what sodium chloride is salt. Table salt, like the salt that you eat. And interestingly enough, if you take table salt and you run electricity through it, through a process called electrolysis, you can actually separate the sodium. So that's what Na is, sodium, and Cl is chlorine. You can actually separate the sodium and the chlorine from each other and make solid sodium. So this would be like a metal, solid sodium metal, and chlorine gas. And if you talk about the properties of sodium chloride, will list some properties. Sodium chloride's white, it's crystalline, it's little tiny crystals. It's pretty inert, meaning that it doesn't react much with other chemicals. So I'm going to zoom in on this just to make it a little bit bigger and clearer. There you go. And sodium metal. So when I undergo this change, sorry, I'm just trying to focus a little. Sodium metal, well, it's a metal. It's silver. And it's highly reactive with water. Meaning if I mix sodium metal with water, it will actually explode or catch on fire. So, you know, salt doesn't do that. Sodium chloride doesn't catch on fire when I put it in water. If anything, it just dissolves and that's it. Sodium metal, though, sodium metal will actually set on fire when I put it in water. And then there's chlorine gas. Chlorine gas it's yellow. It's deadly when you breathe it. In fact, this is the stuff that they make mustard gas out of. Mustard gas is something they use in chemical warfare. So sodium chloride, something that's white and crystalline and you eat it all the time, it's completely inert. I can turn that into something that is a metal, a chunk of silver metal that will catch on fire if it touches water, and a deadly yellow gas that will kill you if you breathe it. I think that's pretty fascinating that I can take this substance and turn it into two completely different substances. And I know that they're different because they have completely different properties than what they came from, this sodium. So here's a little picture of kind of what's happening. So here we have two sodium chlorides. Here's one sodium chloride and here's another sodium chloride. And when I run electricity through it, so I'm just going to draw a little lightning bolt so that you know I'm talking about electricity. What happens is the sodium kind of separates from the chlorine and then groups together. And then the two chlorines actually bond to each other and form chlorine gas. So we get actually two sodiums. We had two sodium chlorides, right? 1, 2. We get two sodium metal atoms, and then we get a bunch of chlorine, Cl2, bonded together. So what happened in the process of me running this electricity through? Well, these guys split apart, and then they rearranged. So these two went together, and these two went together, and I end up with this and this. So you get a separation and then a rearrangement. And that's what's happening when something chemically changes. It's atoms, what it's made of, those atoms actually break apart. So atoms break apart, you know, from each other, not the actual atom breaking apart. And they rearrange to form new substances, okay? So let's zoom out again and we'll go back to our original paper here. So the problem with chemical change is that sometimes it's hard to tell. Like with the sugar going to charcoal and water, that was really obvious that a chemical change took place because you can see that there's completely new substances formed. Sometimes it's really hard to tell because we can't actually see, you know, we can't see atoms rearranging. So even though I just drew a picture of atoms rearranging, we can't actually see that in real life. We can't see atoms. They're too small. So we're going to look for signs that a chemical change has taken place. So, you know, again, we talk about that sugar turning to charcoal or water, or we talk about burning something. Those are really obvious changes, so we can use those as some examples. So there are 5 indications of a chemical change. And not all 5 of these have to happen for a chemical change to have occurred. Just one or more. But if at least one of these things, except for temperature change, and we'll talk about that, if at least one of these things is observed, then you have a chemical change. And so let's talk about each of these. So production of a gas. Production of a gas, like when we light a match, is going to look like it's going to look like smoke, right? So sometimes you'll see smoke. Other times, if it's in a solution like vinegar and baking soda, you'll see fizzing or bubbling. So you know that a gas was produced because suddenly this thing starts to fizz and bubble. Now don't get that confused with carbonated soda. Carbonated soda fizzes and bubbles, but that fizzing and bubbling was there already. Like, you didn't just suddenly, like, you know, put something in there and suddenly it started fizzing and bubbling when it wasn't fizzing and bubbling before. So that's not a chemical change, because that fizzing and bubbling is actually just in there already. We're talking, you mix two things that aren't fizzing and bubbling and suddenly they fizz and bubble when you put them together. That means a new substance is being created, and that new substance is a gas. And again, sometimes you might see smoke instead, or you might smell something, like smell a new smell that you didn't smell before. So a new smell that you didn't smell before, like when, you know, like rotting garbage, right? That's going through a chemical change. The chemical is, or the garbage is rotting, and it's giving off a nasty smell, a putrid smell. All right, color change. Color change is, you know, pretty obvious. If you go, it's yellow, and then it undergoes a change to black, you know, you've got yourself a color change. Be careful with color change and make sure it's not an expected color change. Like, if I take a piece of paper and I draw red, like what I've done right here, I've got paper and I've been writing all over it, and now the paper has gone through a color change because I'm actually putting color onto the paper, that does not count as a color change. A color change is you've got two chemicals and you mix them together and they turn a color you wouldn't expect. Like, if I took, say, sugar, which is white, and sulfuric acid, which is colorless, and I mixed them and it turned black, that is an unexpected color change, because something colorless and something white should not turn black. So that should indicate to you, wow, we've created a new chemical, and that new chemical has a new color, and it's black. All right, production of light or flame, also pretty obvious. You know, examples of production of light. There are lots of animals out there that actually do this. There are mushrooms that will bioluminesce. They have a chemical reaction that takes place in them, and they give off light. Fireflies do this. They have a chemical reaction that happens in their butt that gives off light. Those little glow sticks that we like to give or get, you know, when we, on Halloween or at fairs and stuff like that, those little glow sticks, when you crack them and shake them and they suddenly glow, that's because there's a chemical reaction and that new chemical is glowing. And then same with flame. You know, you light something on fire and it gives a flame off, that means that there's a chemical change taking place. All right, change in temperature. Now, the reason I have a star next to change in temperature is because alone, this is not a sign of a chemical change. Meaning that if you mix two chemicals or you react two chemicals and all that happens is there's a temperature change, that doesn't necessarily mean that the reaction was chemicals or that it's a chemical change. If you see this with any of the others, though, then certainly it's the sign of a chemical change. Just know that, like, something changing in temperature, for example, if I dissolve salt in water and I measure the temperature while I'm doing that, it actually gets colder. But dissolving salt in water is a physical change because I still just have salt in water. So that would not be considered a, I don't really see any of these other signs, so it's not a chemical change. So be careful with change in temperature. It has to happen alongside one of these other changes. Now, formation of a precipitate, we're actually going to talk about later in class, but formation of a precipitate is, I'll just describe it, it's when two solutions, so solutions are something dissolved in water, are mixed, and a solid occurs, so a solid chemical results.